Okay. Now that we've talked about the assignments, yeah, there we go. Okay, cool. Okay, where were we? We were on, so we finished up the 7-segment display. Let me put this on. And we talked about, like, okay, look, we can program all this stuff in. Am I recording good? Yeah. We can go put this in by hand, but it's too much of a pain in the butt, so we built some nice code to generate these hex files for us that we can load into the lookup table that can decode effectively any input pattern to its, where the input pattern will be like the binary number to represent, plus a sign signal. And that'll map to its corresponding 25-bit 7-segment display 3-digit plus a sign pattern. That's what we did. And how did we do it? Very quickly, I made a bunch of constants where each constant stored the bit pattern for that particular digit. I put them in a list such that 0 was an index 0, 1 was an index 1, and so on. We generated the bit patterns for each number by getting each digit's value, using the digits list to get the hundreds pattern. We bit shifted them around, ORed them together to generate the whole 24-bit pattern for unsigned numbers. We did it again for signed numbers, and then finally we just saved the results to a hex file. And I would have something like this. And again, if you remember, let's open it up. Is it still going to be open on that one? No. Oh no, don't look at this. Assignment, oh, that's an old version. That's fine, you can look at that. That's an old bad version of the part 2 of assignment 3. It doesn't, it's useless. Topics. But by the way, that is the general idea of a simple ALU. We've talked about it before. Here, look. A, B, all of the operators are always acting on A and B. So the outputs, this is always not A. This is always OR AB, and AB, XOR AB, add. These are some barrel shifters. Whatever. Don't worry about them. We're not using them. They're kind of a pain. So they're always all being calculated, which is, there's no real cost to calculating them. They don't require clock cycles. They're all like, they just happen, right? They're not sequential. So they're always outputting, but depending on which operator I want, that's the one I output through a multiplexer. They're a big hint for part 2, although I don't think I spoiled anything for anybody. Where's output, output, output? There. So if we go here, edit, this is the lookup table as generated by that script, which, by the way, I have around here somewhere. Where? Oh, that's labs. Topics, output. So here's the code with a bunch of comments, but we already talked about this, okay? And I know we've talked about this before in other classes, if you've had me. If you see these comments, these are just tags, because when I generate the website, it goes and looks for these tags, like copy the code between here and here. So those are meaningless to you. If you want to see the, where's like the hex file? There, here's the hex file, if you care. Of course that makes perfect sense, right? Well, yeah, you know, they represent bit patterns. Cool. So we go there, we hit cancel. Let's put in the number, whatever this number is. 170, right? That's 170. So when the input bit pattern is 10101010, we get that number. These are just probes for testing purposes. If you look up it checks these labels. We won't include them in the system. Really, the input pattern is 010101010, right? And if I change that to this, now it becomes -86. Why? Well, because now it's looking at this chunk of the lookup table that correspond to the signed integers. Cool? Cool. All right, there's the review. Any last questions about this? And yeah, here, we can go edit. See, these are the labels for the testing purposes. It's just verifying that the outputs of these match. Because I can't test these. Because again, these are side effects, right? We have a system with a side effect. Like an output really is like, it's weird. Cool. Last chance for questions before we move on. So, now the question is, how do we add this to the system? Well, remember with like the address register, because the data on the data bus, like if I want to specify a RAM address to put data into, I have to put the RAM address on the bus, which needs to go into RAM to reference a specific RAM address, and then it needs to get data from the bus. But the problem is there's the address on the... So what I do is I put the RAM address in a special register so it's isolated from the bus and can stay there for as long as we need it. And it references the memory address, and then the data on the data bus can change because the RAM address in the address register is isolated, and it's fine. Now the data on the bus is it's always changing. And don't get me wrong, the data in the address register is always changing too, but not like the data on the data bus, right? The bus is always like changing information, whatever information's on it. The address register is going to be, the data in there, it's transient, but not as much. We change it when we want with intentionality. The data bus is always changing. Similarly, we're going to do the exact same thing with the output register. We want to output some data. Well, we can't just output the data on the data bus because the data on the data bus is always changing. And so that's no good. I want to output specific data. So I take the data I want to output, put it into a special register, and it displays the output like with that 7-segment display design that we already did. We can change the data we want to output by changing whatever data is in the output register, but the point is we isolate it from the data bus. Clear? Cool. So we're going to create this like output module that contains the output register and the 7-segment display patterns. So we're still going to use that lookup table design. We just need to, separate the data with a register. We're going to call this the output register. So here's the general idea. Okay? Now, let's pay special attention to what's going on here. In fact, this right here, this design, oh no! This has all the, I have to go and regenerate this picture. Look at, it's got all the dots. No, it's not. I appreciate you trying to make me feel good, but it bothers me. Wow, okay. So, pay special attention to this design because I actually had to go back and I spent so many hours fixing this because I designed it wrong. And I designed it wrong in like December. And then like midway through January, I realized my mistake and I had to go back and change all this crap. It was such a nightmare. But this design had a big flaw, but it's fixed now, in spite of the dots. So, what's the same? Okay, we've got these here for testing purposes. Again, we're going to remove them by the time we add them to the system. We've got our lookup table, there we go. And we've got our 7-segment design here. Cool. All I've changed is the fact that I've added the register. And I've got that general design where like, oh, here's the bus. Data inputs, outputs, clocks, and some control signals over here. Right? This is the general design we've done whenever we've created like a module that will later be added to the ESAP system. So, first, okay, clock is hooked up to clock. The output enable, that is like, okay, enable this output register. Like, will I put it, like, is it ready to read? Cool. Notice, when you look at this design, how many data bits must this register store? Or must. How many is it storing? This isn't a trick question. You should be able to count to this number. 9. There's 2 ways you can know. One, we'll look at the output, right? 0 through 8. That's 9, right? we remember that, okay, yeah, we needed the 8 bits plus the sign bit, or sorry, well, the sign control signal, which, yes, that like 8th bit, 9th bit was a bit in the sense that, okay, it was a signal that was high or low. Its meaning was different. There were the 8 bits here, 0 through 7, that specified the number, and the 8th bit, 9th bit, represented that like control. Well, was it signed or unsigned? Okay? So yes, it's just another bit, but it has different meaning. And we can see here we've got the 8 bits from the data bus, but it's being merged with the sign bit. That sign bit needs to be stored. Okay? And it needs to be stored in here with the clock pulse. Think about, it might be hard to see at this stage, but if I were to say, imagine this sign bit didn't get latched and stored in the register, and it was just fed into here, like this, which was the original design I had, which was majorly flawed. If I stored the value that I wanted to output in here, but not the sign bit, and I were to say, okay, output the signed number, negative, what was it, 86 or something, right? If I were to say that, I would have whatever the bit pattern is here for negative 86, 2's complement, and that sign bit would be high, right? Now, the next thing I want to go calculate is maybe I need to go do some addition, right? Remember how we did the ALU, and then we start manipulating the control signals for the addition. Now, I don't need that sign bit anymore for addition, so I set that sign bit low again because I don't need it. Uh-oh. The output value changes back to the unsigned version because the sign bit was never set. No, the sign bit must be stored at the time that we are saying what is the value we want to be like outputting. We need to store it. Cool? Cool. So here's the general design. There we go. It latches on a clock pulse Q. Yeah, there we go. Cool. Hopefully it's clear that this is just the same design as before, but we hooked it up to a register, which was hooked up to our like isolated data bus type thing. Any questions that we see here? All right, so with the design, one can control when data is loaded in the output register for displaying. As discussed previous topic, the sign signal controls when the output's 2's complement. Remember, the signal is ultimately the input, like whatever. Okay, yeah, we just talked about it. It is important that the sign control signal is included in the output register as a 9th bit, 8th bit, 9th bit, depending on if you start counting at 0. Yeah. This is what I was just saying. However, remember that the 9th bit is not part of the data to be output, but storing that like signal state. I know I'm a broken record when it comes to what do the bits mean, but this is very important. Because when we're dealing with these low-level systems, it's our responsibility to remember what all of these bits are and what they mean. It's not until you get to higher-level languages where the programming language takes care of a lot of these things for us, where at this low level, we, as the programmers, as the designers, need to be aware of this stuff. So how do we add it to the system? Okay, well, let's just throw it in there. Boom. I effectively copied that design, pasted it right here, included the control signals down here so they're in a nice, consistent, collected area. The order of these things is, although arbitrary, it is by, when I say arbitrary, it doesn't really matter the order that they exist, but I included them in the order that they exist for design purposes, so it looks a little nicer. That's all. And yeah, there we go. We hooked that up to the data bus, the clock, enable signal, and the sign signal are down here. I think I changed this to output I instead of output enable, but it doesn't matter so much. Cool. There we go, look at that. Now, our design includes RAM and the address register, which we've combined, two registers, A and B. These are our general purpose registers. The ALU that will calculate the addition or subtraction, depending on the signals, of whatever's in A and B. And now we have an ability to output stuff. So now we can put data in RAM, load them up, calculate some number, and then actually output it in a nice readable way. I think that's pretty cool. So like before, yeah, there we go. And so here's the comparison, right? All we have, so this is that again, overview idea, clock, RAM, address register, two registers, the ALU. Now we have an output register and display. There. And our data bus. I think I've said this before, but note that this design over here does not include the control signals, obviously, as you can see. Why it doesn't include them, I don't really know. I don't really know how they would show that, but they're not there. This general design here did also, I don't know if you really noticed, they do also include directed arrows. This is showing that, like, well, the output register can read from the data bus, but it can't write to it. It doesn't really make sense that it would. Input, output, address register. The address register can read from the data bus, but we can't put information onto the register from the address register. It doesn't really make sense. The only difference here is the B register. Here, it's designed such that B can only read in, and it can't output. Our design can output from B back to the bus. Okay? We did talk about this before. Does anyone remember why B in this design didn't put information back to the bus? Or why was it okay not to? We all agree, like, okay, more flexibility is more flexibility. Why not, right? Now, why one might not want to is, well, with more functionality comes more hardware. And if you're physically building this, costs and whatnot, whatever, right? But like, why would I not want to? Well, really, we have RAM. Like, we can read and write data to RAM. And we have registers. So if you're like, oh, we want more registers to store more information, well, you can use RAM to store information too, right? So not that big of a deal. We only need the registers as like a temporary holding place. In fact, with this design, the B register, for the most part, is used to add information to A, like with addition. So like, you could design it where instead of being like, put data into B, output A, or output from the ALU, you could say like, the way to add to A is to just put information into B, because B is only there to like add to A and get information out of the ALU. But our design, we added a little bit more flexibility. All right, so, let's run a program on the system. You'll start to notice this does get a little tedious as we're controlling all these input signals, but let's do it anyways. Physically programming these systems, yeah, is tedious. There's got to be a better way, right? Well, don't worry, there is, but we'll get there. We're working our way there. So what am I saying? Okay, load 15 to the A, 4 into B. Okay, cool. Let's open output register there. So here's that design. Great. Run. Can I go in here and edit these values? I can't. Okay, let's just lazily, I'm not going to like load 0 into the data line. I'm just going to put the values 15 and 4 into RAM, okay? So we don't have to do it manually. So I'm cheating a little bit. So let's put OXF. Well, I think if I just do F, it'll probably know. No, OXF, there. And then OX4, there, cool. There, I've just put 15 and 4 in RAM already, so we can save that step. But if I really wanted to, I'd put 0, let's make sure it stays. Okay, good. I could put 0 here, load it into the address register, then put 15, load it into RAM, then, I'm just skipping those few steps. Okay, great. So So, okay, we've got 15, 4. So what do I want to do? Okay, 0 is already in the address register, so we could skip that. So I want to take the contents from RAM and put it into A. So let's put 15 into A. Okay, so how do we do that? Well, RAM, man, it's getting hard to see, eh? RAM, man, forgot to set those things to Z. All right, well, let's try that again. I'm going to have to go up here again, aren't I? Yeah, F, okay. All right, so set these to Z. RAM out, A in, right? Clock pulse. Then I need to put, okay, let's turn this off. 1. One there, and we'll do address in. Geez, this is tedious. Clock pulse, so now there should be a 1 on that line. Yep, okay, set these back to Z. Ooh, that was close. Okay, so from that address, we're going to say B in, RAM out, clock pulse. Okay, now we can go down here. Okay, B out. There we go. All right, now what do we want to do? We want ALU out, and we'll put it into the output in. Right? Sound good? Because what should be here? Well, it should be F plus 4. Right? Makes sense. Clock pulse. So what is 15 plus 4? 19. Come on. Hey, look at that. Look at that. We just programmed in the most painful way possible, adding 15. And oh, let's go crazy. Fortunately, this is pretty easy, actually. Let's do the subtraction. Let's just do it again, but this time, okay, subtract, right? Notice that by changing it to subtract, it didn't change anything. And notice that changing sign doesn't do anything until a clock pulse, because sign doesn't get latched into the output register until there's a clock pulse. So 15 minus 4 should be 11, right? Nice, cool. So in a very tedious way, we were able to tell our system to add 2 numbers or subtract a number from another, right? All we had to do was, now interestingly enough, actually, I never actually had to input data. I mean, I suppose I had to input the address values as data, but is that data, is that instruction? That's a little bit kind of in between. But I never inputted the value 15 or 4 through those data lines. I was able to add them to RAM pre-hoc, okay? Yeah? And then all I had to do was control the signals for, like, okay, the RAM addresses I needed to do. But otherwise, it was just manipulating these control signals to move data around, right? Pretty cool. And then we outputted the data, and we can see it with a nice output display now. If you don't, like, get excited about this, I don't know what you're doing, because I think this is fantastic. And to me, what I really want you to see is that, like, look, we started, we're not done. We still got ways to go in the course, right? We've got 5 weeks left. But I really hope you're seeing that we started with transistors, okay? And you think, like, how do these sophisticated computers work? This is how. It's just a lot of this. There's really, like, all we've added is additional layers of abstraction. Like, okay, it's easier to program, But the underlying concepts, like we know how it works now, okay? That's how this all works. How do these computers do it? By moving crap around. That's it. Add things, perform some basic logic, move data around. That's how you get a computer. That's it. And we were able to do it. We built one. Obviously, what is this computer missing? Well, it'd be great if it could kind of control itself, right? Like when you write a program, you write code to say, okay, go print something, and then you hit run and it does it, right? Here I had to go and like physically manipulate these signals in order to add numbers and output it, right? Like, okay, I couldn't just say like, okay, go output something, run, and then it would go do all that stuff for me. Because you can imagine like when you tell Python like print hello world, print 15 plus 4, run. There's a couple of steps going on, right? And we can see what we had, okay, move data from RAM into there, move data from RAM into there, output from the ALU, put it to there. There were a couple of steps. Obviously, Python's doing a couple of steps. So there were some amount of this going on a computer somewhere in order to do that. We had to do it here. So wouldn't it be great if like the system could kind of like do that on its own? Like I would tell it, okay, go add 15 and 4, run, and then wouldn't it be great if it can kind of just like go do it? Instead of me having to go manipulate this? I mean, that's like a huge part of what we're missing here. And that's where we're headed. But as of now, like we can control this system. The system is controllable to perform computation. It doesn't have a way to control itself. And you've probably noticed in like other courses, like I like to talk about this in 161, 162. It's always like things get interesting when they become self-referential. When something has the ability to reference and like manipulate itself. That's always very interesting. And that's an important feature in computation. But it's also where like things get weird in the universe, right? Like we play those games of like, this statement is false, right? Well, that's a bit of a puzzle, because what does that mean? This statement is false. Someone explain to me, what does that mean? Well, you can't really, because it's not really explainable. This statement is false, so is it true or false? Well, if this statement is false, that means I shouldn't believe it, which means if it's not false, it's true. That means it's true, but if it's true, it's telling me that it's false, and if it's false, that means it's true, which means it's false, which means it's true, which means... We get a little bit of a pickle because the sentence, this statement is false, references itself. That's where things get weird, but that's also where we get the power to do like automated computation. Right now, the system lacks that ability to really manipulate itself. Other fun ones like this is like when Pinocchio says, my nose will grow now. What will happen to Pinocchio? If it does grow, he was telling the truth, which means his nose should not have grown. I mean, you can make it make sense if you're like, well, what if he lied and then said it? Okay, look, stop trying to beat the question. What will happen when Pinocchio says that? If his nose grows, that means he was telling the truth, which means his nose should never have grown in the first place. If it doesn't grow, that means he was lying, which means it should grow, which means he wasn't lying, which means it shouldn't grow, which means Pinocchio would be in trouble if he said that, right? Like that'd be a bit of a problem. There's a number of other funny little ones like that. Who here remember me talking about autological and heterological words? Yeah, that's another like puzzle, right? For those of you know what, I'll say it again because only like 3 people raised their hand. Let's say we have, like, look. I want to be able to take every word and classify it. Why? Because I'm a human and we like classifying things. It's something that we're obsessed with. So how about this? I want to take every word and put it in one of 2 buckets, okay? Either the word goes into the bucket labeled autological, which is a fancy way to say the word describes itself. Like the word English is English, so it's autological. Pentasyllabic is pentasyllabic, so it's, you know. If I were to write the word black in black font, it's okay, it's black, fine, autological, right? All words that are autological go into the autological bucket. And then everything that's not autological goes into the heterological bucket. It doesn't describe, it's not, right? It just doesn't describe itself. So like chair. Is chair a chair? No, it's the word, it's a word, it's heterological, right? Is the word like unhyphenated, assuming there's no hyphen in it, autological? Yeah, it's unhyphenated is unhyphenated, it's autological. Is the word computer a computer? No, it's heterological, right? So you give me a word and I put it into a bucket, right? And you just keep giving me words. I put it into one of these two buckets. Presumably the heterological bucket's going to be bigger, but whatever. You give me a word, it goes into one of these two buckets. Is this a reasonable task that I could give somebody? Right? There's nothing outrageous about this request. It's kind of annoying, but I could ask someone this question. And then eventually, the word autological comes, and I have to ask the question, is the word autological autological? I guess so. Like, is autological autological? Yeah, it describes itself. I guess it is if it is. It isn't if it isn't, right? Is autological autological? Think about it. Does the word autological describe itself? Well, autological means the word describes itself. And it only describes itself if it describes itself. I don't know, that's a bit of a thinker, right? It's a bit of a puzzle. So where should it go? I guess it doesn't really matter, right? Is autological autological? It could go in either. If it goes in the heterological bucket, I guess autological doesn't describe itself. Okay, fine, whatever. If I put it in the autological bucket, oh, I guess it describes it. Fine, whatever. It doesn't matter. There's no wrong answer here, which is kind of a puzzle because, like, well, I wanted to put each word in one of these two buckets. So which bucket should I put autological into? Well, I don't know. All right, whatever. Let's say it is, okay? And now you give me the word heterological. It's the last word. I've done every other word. It's been nicely classified. And you give me the word heterological. Where do I put it? Which bucket do I put the word heterological in? Do we see the problem? Well, let's say heterological doesn't describe itself. Hold on. If heterological does not describe itself, then it's kind of describing itself, right? If the word heterological does not describe itself, that's the definition of heterological, right? Which means it is describing itself. So it must go over here, which means it's describing itself. But if it's describing itself, it's heterological. And it should go back over here. As soon as we get into systems where you introduce self-reference, you run into problems. But that's also where you run into, like, power. That's also where you run into, like, the ability for, like, computation to happen in a good way. So that's what we're working towards. Whoop. Any questions about this design? And what would happen if I were to say it's signed and we output this? Well, nothing really should change because the number is the same, signed or unsigned, because its leading significant bit is the 0, so it doesn't really matter. All right, here's me showing you how to run this program, how to set all of those control signals, including the data inputs. There we go, cool. Cool? Next, program counter. Okay, so the next thing we're going to cover is a counter. Well, we just built a counter in assignment 2, but we're going to do a program counter in a different way. Now, the program counter is an important step towards having the system able to manipulate itself. The general idea is, look, when you think about, I know I like to design courses where we discover how things work as we go along the way, but I recognize that most of you have used a computer before, and we kind of have an idea of how things work, right? And when you run your code, you know things happen in like sequential order. There's like an ordering to which things happen. You do this instruction, then you do this instruction, then you do this instruction, then you do this instruction, right? Right. Now, when we program in a high-level language like Python, we've got lines of code. But we also know that there's like this compiling step. Now in Python it's interpreted, whatever, fine, it's different. But if you're using like a language like C, you compile your code that runs on the computer. And there's a mapping from your code to the instructions that go into RAM that your computer executes. But it's not a one-to-one mapping, right? You can't look at one line to one line. There's a little bit of extra steps involved, right? There's a process of compiling. But at the end of the day, there's still this step, then this step, then this step, then this step, then this step, okay? The program counter keeps track of which step we're on. In fact, it keeps track of the next step that we should execute, but more on that tomorrow or Thursday, whenever we have class next. All right, I'll see y'all later.